Okay, go.
All right, a magnet has a magnetic field, and the symbol for the magnetic field is a capital letter B. Don't know why. And we saw this with the iron filings that we did a while back. Come on.
I know. It's like if it even leaves that frame, it forgets what it is.
Okay, the iron filings line up on the magnetic lines of force in the field. So these lines are called magnetic lines of force. And the picture that these lines of force provide is called the magnetic field. It's a region of space around a magnet where it can exert a force. Okay, we're good with all this stuff. A compass detects the presence of a magnetic field. That's a thing. We had the electroscopes that detect the presence of an electric field. Compass detects the presence of a magnetic field. And the magnetic field is a vector quantity. You can have a strong field or a weak field, and the direction of the magnetic field is defined as the direction of the north on the compass points. Remember, we got the bar magnets hanging over there, and the north side points north, and the direction of the magnetic field here in the classroom is towards the north. Okay, and it's out from the north and into the south. Why? If you hold a compass here, the north will be repelled. If you hold a compass here, the north will be attracted. And everywhere in space around that, the direction, the orientation of the compass shows the direction of the magnetic field. And magnetic fields interact to exert forces, which leaves some interesting questions here. Opposite poles attract. Okay, and this is what we saw this with the iron filings and the bar magnets. And
pumpkin.
I call this the pumpkin, right? Okay. And for attraction, what directions do the two fields have between the magnets? What do you mean? Well, there's the magnetic field to the south, and there's the magnetic field due to the north. And what can you say about the direction of the north's magnetic field and the direction of the south's magnetic field where they're interacting?
They're all.
Here's the direction of the north from left to right. Here's the direction of the south.
They complement each other out of the north into the south.
Direction.
Yeah.
Okay, so when the fields are in the same direction, you get attraction.
Got it.
Okay, same poles repel. Completely different picture here. And here we have two norths, and the question is, what direction do the two fields have between the magnets for repulsion?
So they're opposite there.
Well, they're in the same direction. I beg your pardon, you're right. They're in the opposite direction.
Yeah.
This one's going this way, this one's going this way. They're in the opposite direction, they repel. That's a very important thing.
Okay.
If the fields are in the same direction, attraction, opposite direction, repulsion. Okay, so the direction of the interacting fields show the attractive or repulsive forces. So that's the big idea for today.
Okay.
When the fields are two, and there's some overlap here, the direction determines attractive or repulsion. Here the directions are opposite. Here they're the same. Attraction, repulsion. Wire, battery, and compass.
La da da. You can barely see that wire on there. Let me.
This is called bell wire. It's a thin wire that's covered with varnish. And what I did is I took a piece of sandpaper and I took that, because that serves as
varnish off.
Well, for insulation.
Yeah.
Okay, so I've got the compass here on the table.
Put the compass on the table and place the middle of the wire over the compass
Perpendicular. Okay, so I don't have this perpendicular. I'm going to have to make it perpendicular like this. Get down there, you get
Perpendicular to the.
to the needle.
Oh, okay. I see. Let's see.
Okay, perpendicular to the needle. Let's run an electric current. Sure we are. Nothing happens. Okay. Now place the middle of the wire, and see, the reason I'm using the tape is if you have students, you got two students, each has a pair of hands, they can hold stuff in place. this here. And now, when we run a current through there,
Ha ha ha. Okay, so the arrow points towards, the arrow is the electric field, so that means electric field.
magnetic field.
Magnetic field. So that means
That
it's
underneath the wire, let's see here, it says, the compass detects the presence of the magnetic field around the wire when current flows through it. So no magnetic field, no current, current, magnetic field. Ouch.
Oh, gee.
Sucker gets hot fast. Okay, here if the north end of the needle points in the direction of the magnetic field, what's the direction of the field under the wire?
at the north end. Which one is the blue?
That
North?
blue is north. So it's underneath the wire, it's going
Go
that way.
Yeah.
Okay. All right. So turn the battery around.
Wow.
What
And now
happened?
it's the opposite direction.
Now it's going in that direction. So what happens when you turn the battery around in the current of the wire?
It just changes directions.
It changes the direction of the current.
Yeah, the current, yeah.
And so changing the direction of the current changed the direction of the magnetic field under the wire.
And it went that way now. I was pointing that way.
Okay, so I'm going to go back to where we had it before.
Okay.
Come on. Come on. Okay, so now we've got north that way under. All right, so now I'm going to take this out.
Put them on top.
Yep. Put it on top. And now it goes in the opposite direction. Okay, so what does that mean?
That means that it's not it goes all the way around the wire.
Yep. So the direction of the field on top of the wire is that way. The direction of the field under the wire is the opposite direction. And you're right. What's the relation between the direction of the current and the direction of the magnetic field? Well, here we've got our original. And so it's on top. And if I turn it around, it'll be in the opposite direction. Okay, so current is charge moving in a wire. And there's two things going on, of course. You've got the actual electron flow, which goes from the negative to the positive. But then you have conventional current that goes from the positive to a negative. So here, with our original thing, I've got... So conventional current is going from the positive towards the negative around like this. And so there's a relationship when current flows around a magnetic field appears around the wire. The current goes away, there's no field. But notice the shape of the field there.
Yeah, circular, right?
Yeah, and what you've got, circular. And here's a
Compass,
here's a compass needle. And, well, we'll get it.
And I mean, this picture might be all.
Okay, magnetic fields have a shape and a direction. Out of the north into the south. The shape of the B, the magnetic field around a wire is circular. So you've got current going this way from the positive to the negative. So this is conventional current. And you've got a magnetic field that's circular around the wire. So that's the shape of the thing. And the direction of the field is shown by the first right-hand rule.
Oh.
The first right-hand rule is this. The thumb shows the direction of the current and the fingers curl in the direction of the magnetic field. The thumb points in the direction of the current and the fingers curl in the direction of the magnetic field. The wire is straight, that's your thumb. The field is circular, that's your fingers.
Okay.
All right, so let's go back to this.
Bada boom.
So conventional current is going this way. So underneath, come out of there, you dad, blame you. Don't make me stop this car. Come here, you. Have you
Here,
got
let me
finger?
see.
No, I got fingers. I get it.
Like,
I get it. All right. Okay, so if the current is going this way, underneath the field should point to the right. And it
Let me
does.
see it.
So that's underneath. The current's going this way. It's to the right. On the top,
It'll be
that
like
way.
that way, yeah.
So that's the first right-hand rule. The first right-hand rule.
And that's familiar.
The lefties, Canadians, I used to have a video that was made in Canada. You could tell because they'd say a boot instead of about. Okay, they think that there are electrons moving in the wire, and they have a left-hand rule. So if you think about it, you've got the right-hand rule for the conventional current, but the left-hand rule will give you the same thing for electrons.
Gotcha. Yeah. Okay.
So left, I think it's in the next one here. Left hand for electrons. Left hand for electrons.
Bleeding Canadians.
What's the relation between the direction of the current and the direction of the magnetic field around a wire?
Perpendicular.
It's given by the, well, you're right. The planar, if this is the wire, then the magnetic field in slices is circular. But it's like a big long sausage. Well, kind of like this. And so, in fact, if we had current flowing in the slinky from south to north, then the thumb would say the current is this way. On top, the field would be that way. On the bottom, the field would be this way. So it would go around. Looking toward the clock, it would be going around clockwise.
Yeah.
Right?
Well, hiding the battery. Use a compass. Hiding the battery. What does that mean?
Okay.
I was like, what?
So I've got
The real use for the mask.
I've got the battery here, and the wire is underneath. Let's see if I can do this. Don't look.
We use a compass to tell the direction of current in the wire. Okay. Not looking. Okay, so it's that way, so the current must be going this way.
Correct, mundo.
Right? Now, when I say current, I mean conventional current.
Well, current and electron. So we'll use electron flow or current. Oh, wait a minute.
Is that it?
Should be more than this.
Here you go, looking. Scroll down a little more. Is that everything?
Yeah, that's it.
Oh.
But here's the deal.
Yeah.
There's a lot more.
I know there's 2 more rules, right?
Yeah.
I know there's this one. It's like with the it's like with the velocity and the force, so the field is that one. What time is it? 9?
Yeah.
8:55, sorry.
My vaccination is at 9:45.
9:45. So I feel like I understand. You want me to keep recording?
No.
Want to pause? So first right hand, the thumb shows the direction of the current.
Yes. Fingers curl to show the direction of what?
The magnetic field, the B.
If the hanging slinky has current moving toward the clock, what's the direction of the magnetic field on the top?
Towards that way.
Yeah. Okay, and there's your first right-hand rule. Okay, since the direction of current in wire is perpendicular to the magnetic field around it, we need a way to symbolize things going into or out of a page. If you use an arrow, if you shoot an arrow, you see the X made by the feathers as it goes away from you. Okay? We'll use an X to symbolize the current or the magnetic field going into the paper away from us. If the arrow is coming toward you, you better duck. All you see of it is the shaft. It's the dot of the shaft coming toward you.
Good God. I hope
Okay,
that's not
so
you.
we'll use a dot to symbolize it coming out of the paper tortoise. I had a wonderful video, and I threw the cassette away. And I had all those cassettes.
Yeah, I feel like you always say that. I'm like,
Okay, so let's just, for a second here. Here's a wire. And what direction is the current going?
The current is going
into the board.
Yep.
Okay. So if the conventional current is into the board, what's the direction of the magnetic field around it? Clockwise or counterclockwise?
Clockwise. Yeah, I was like, it's like this. Clockwise.
I know. Okay, so if I have a wire like this and a dot, what direction is the current?
Counterclockwise.
Well, the current's
coming out of me.
But you're right, it is going to be counterclockwise.
Yeah.
Okay, if I have a long wire like this with the current going this way, what direction is the magnetic field on top?
It's coming towards you.
Okay, dot or X?
Dot.
And on the bottom, what direction is
X.
it going?
X is going in.
So this is the symbolism for direction.
Cool.
So if I have current going in this wire in that direction, the magnetic field is going to be like this, yes? What happens to the magnetic field when I make a loop?
Oh, they're going to be interfering with each other.
Okay, so it's like this all the way around, right? And what do you notice about the direction my fingers are pointing?
They're always going towards you. In.
Very interesting geometry. When a current carrying wire is looped, the magnetic field loops well, gives you a donut shape.
Yeah.
So here we've got the current going this way, and you can see they have everywhere around the loop inside the magnetic field is going in.
Yeah, okay.
Also, an important thing to notice here is where are the fields closest together?
Like all of them interacting together in the middle?
Exactly.
Yeah.
And where are they farthest apart?
On the outside.
And that tells you something about the intensity of the magnetic field around a loop of wire. On the inside, it's strong, and on the outside, it's weak. Okay. Use a first right-hand rule to find the direction of the inside the donut hole. We just did that. Okay. Coiling wires through many loops makes a coil or a solenoid.
I've heard that before.
Okay, so now notice here those are X's and those are dots.
Oh, okay, I see.
So the current is going, see this is an X and this is Google, I've blown it up. Okay, so here the current, wait a minute.
It's going this way. Yep, so.
Yeah,
so it goes in. Yeah, so it's
wait
going.
a minute. You've got the field this way, so, I can't tell this.
Wait,
which one is X, which, well, the magnetic field is this way.
Oh, wait, so that means that the B is the.
So, check it out. The magnetic field inside to each coil is in the same direction. That's the important thing here.
Wait, say that one more time?
The magnetic field inside due to each coil is in the same direction. And each coil that you add increases the magnetic field inside.
I see. The coil is a loop, like it's the yellow. The coil is
I've got a better illustration right here. Okay.
Oh, okay.
Here's the magnetic field inside due to each coil is in the same direction. This is a better one. It shows you the direction of the current. The current is coming down like this, and it's wrapping around.
Yeah, okay.
So now, what's going in a circle? The current. What's going in a straight line? The magnetic field. This is the second right-hand rule.
Because as you follow that thing along, it looks like this, and it's donating.
Well, yeah, okay, so that's a good point. The first right-hand rule allows us to figure out the direction of the field due to one loop. And if you've got a bunch of loops, they're all in the same direction on the inside. The current's going around.
Okay,
like
that makes sense. It's all because if you go back to that green one, that first visual you showed me,
Yeah.
they're basic. I keep going to the other green one. I keep going. This one, they're all it's just a straight line down all
Yeah.
those loops that are
Yeah.
imaginarily
Exactly.
existing there.
Exactly.
Okay, that makes
So
sense.
now inside, the magnetic field gets stronger with every added loop. If you make another loop,
Yeah.
it makes the magnetic field stronger. Okay, so the second right-hand rule, this is the second right-hand rule for coils. The fingers curl in the direction of the current,
Okay.
and the thumb points in the direction of the magnetic field. The
For
first and the
coils.
second rule look the same.
Yeah.
You have to ask yourself, what's going in a circle, what's going straight? Here, the current's going in a circle, and the field is straight.
I see.
So now, the field is like this. So this is like the north end of a bar magnet. This is like the south end of a bar magnet. Okay? And so here you've got another one. This time, hold up. They've got the current going like this. Oh, you know what it is? This is a very bad drawing. Because what you should have, one of these should be on the front, right?
Yeah.
And in fact, this one should be on the front, and this one should be in the back because the current is going around.
So you can tell what direction it really is
Yeah,
there.
yeah. So that's a poor illustration.
Yeah.
So that's the second right-hand rule that allows you to show the relationship between current and magnetic field for coils.
How could you use the second right-hand rule to predict which end of a nail with wire wrapped around it would be the north end of a magnet?
Okay, and
Okay, so this is the part that I'm like, okay, so when I'm talking about it's the conventional current, so conventional current, okay. So essentially, second right-hand rule, yeah, be north. You'd have to use a compass, right? Depends on how. Okie dokie.
oops, got the wrong one. So here's the wire. Here's a nail. And I can either wrap it this way or this way. I'm going to wrap it this way. I'm going to start with my thumb like this.
Yeah.
Every wrap will make the magnetic field stronger. Okay. All right. So if I connect this end to the positive, and this into the negative, which way will current flow?
Okay, so we're talking about current flowing. Wait, this end is connected to the
Let's say
negative?
this is positive,
Okay.
this is negative.
No,
Which way will current flow first?
Conventional current is going to flow this way.
Yes. So which direction should north be?
And north will be up there. Wait, okay, so that's the part that I'm okay, north is, it's the opposite of what you think it would be. What's the relationship between the direction of the current? Oh, it flows to the north, not out of the north.
We got
and
two
into the
things
south.
going on. The current is in the wire. The current is in the wire,
Yeah.
which makes a magnetic field. If I had a bar magnet, if this were a bar magnet, you'd have a bar, and you couldn't see what was inside. But you'd see the magnetic field coming out on the north side like that.
I see.
And you'd see the magnetic field going into the south side like this.
Yeah.
This acts like a bar magnet.
Okay, and it's because the magnetic field is going that way, and that's the.
All right, so I'm going to connect this to the positive, like this, and I'll connect this to the negative. All right, see, so it's repelling the north and attracting the south. Ouch,
Oh,
it gets hot.
Jesus, scared me.
It gets hot.
Yeah, I was ready to
Okay,
go. What's gonna happen?
So the field is going like this. The current is going through here.
Yeah.
North was there, and it was attracting the south.
Yeah.
So the idea is, after we've done all this, you have the kids do this.
Oh, so after you did that with them. Okay, because I was like, what does this look like?
No, before I do that.
Oh, you have them do this, and then you show, you show them.
You say, here's a nail. I'm going to wrap some wire around it. What's the direction of the North Pole going to be?
Yeah. Okay, wait, let me try it. Let me hold this real quick. Okay, so you wrapped it around that way.
Yep.
Okay, you wrapped it around.
It's really, no, just pull it straight off.
Straight
It's
off?
fine. Then you run your fingernail
So
around
if I wrap it this way, that's the opposite direction?
That's
Is
the
that-
opposite
is that the
direction,
opposite
yeah.
right? Okay, so I'm wrapping it. The more coils I wrap it, the stronger my electric field will be. Okay. So I've got this going on here. Okay, here we are. And so if I connect this to, if I make the,
Before you hook the battery up,
yeah.
which direction is going to be north?
So this is the negative, that's the positive. We're talking about current.
So current will be
So
flowing
positive
the
that way.
end here.
So it'll go like this. So the north end of the magnet's gonna be this side.
Yep.
Okay.
And all you did was change the direction of the coil.
Yeah. Okay. That makes sense.
And that's it.
Bada
So
boom.
first law, second law,